Hi, in this video I'm going to show how to regenerate the example from week 3 earlier this week, and I had the feeling that for many of you it was probably a bit too fast, so we'll show it again and we'll go through this step by step, and we'll set this up using the color template that we went through today in the class. So I'm actually going to start with a new file from scratch. So here you can see this is my file. I just set up the template, putting in my name and the name of the file, etc. And I also set up my instructions. And I would recommend that when you at home go to recreate this tutorial once more to practice it, that you just copy and paste these instructions and then start from scratch. So basically the goal of this tutorial is to create a surface in in Grasshopper from 3 curves that we will loft through in Rhino. Then we will use the subdivision command here, and we'll subdivide it into a 2-dimensional domain. So that means every surface has a 2D domain. So we have the U direction and the V direction, and we can specify how many subdivisions we want in the U direction and how many subdivisions we want to have in the V direction. So if this were to be set to 20 by 20, that would result, of course, in 400 surfaces. But it also slows down the computer. So I'm going to set this to a smaller number. So once we have created all of our, in this case, 200 subsurfaces, these ones are called subsurfaces, we will then find the centroid of every surface, which will provide us with a list of 200 points. And then at every of these centroids, so you can see again, every of these green points here, which is the center point of the 4-point surface, we're going to find out the surface normal, which is we're going to find out the direction of the surface at that point. So in order to do this, we're going to use this component here, which is called evaluate surface, and it will return us a vector, a normal vector, at that particular point. And then we're going to multiply that vector by a certain amplitude, which is a variable here, which will then allow us to copy the centroid to the end of that vector. So basically we're moving the point from here to here using the move command. And lastly, we're simply going to extract the 4 corner points of every surface, and we're going to connect them to that one centroid here. So here we're taking in all of our subsurfaces, we're exploding it so that we're finding 4 points each, and then we'll connect those 4 points to that endpoint here that we just created, and this gives us this kind of pyramids. And lastly, we'll show a couple of examples of creating very simple analysis. So in this case, we're using the area value of every surface, and we're using that to color code the surfaces. So the larger surfaces in this example are blue, and the smaller ones are red. Okay, so all that. These are the instructions, and we'll start now from scratch. So again, our first step is to create a base surface by lofting curves from Rhino. So we'll start using the Rhino input color. So right click here, make color default, and I will create a curve parameter. Right click on it, set multiple curves, and I select 3 curves from Rhino, or however many you have, and click enter. So now I have in here 3 curves, and now I'm going to group this, and it's going to group it in the same color that we just selected, and I call this RH underscore for Rhino input, for example loft curves. So the next step is to create a lofted surface. Any surface commands are always on the surface tab in Grasshopper. So I'm going over to the surface tab, and in here under freeform we can find a loft surface. So it's not just a primitive surface, it's actually a freeform surface. So this component has 2 inputs. I put my mouse over, and it says it's asking for section curves, and then it's also asking for loft options. So I can ignore the loft options. I'm just going to put in my section curves, and there you go, it creates a lofted surface. Actually, if I put my mouse over the output here, it looks as if it's creating a B-rep, a boundary representation, which looks like this component here, right? B-rep. But in fact, if I put my mouse over, you can see it's in fact creating an untrimmed surface. But just to be sure, so the next component that we're going to use, the subdivide surface component, only works with surfaces. So in this case, I can actually use the surface placeholder to convert the B-rep into a real surface. And again, it just says untrimmed surface. So it's really not a B-rep, it's an untrimmed surface that comes out of the loft command here. So now that I have my lofted surface, I'm actually going to start labeling this a bit. Actually, I'll label it in a minute. So now that I have my lofted surface, the next step that I want to do is I want to subdivide it. So I'm going to the surface command, and in utility we have something called isotrim, which will give us subsets or subdivisions of a surface. So it has two inputs, and you can already see in the preview, this is basically what we want. We have kind of our larger surface, and we just want to create these smaller surface elements. So of course it's asking us for a surface as an input, and it's also asking us for a domain squared for a 2D domain. So here's our surface, and now we have to set up a two-dimensional domain. The reason why we need to set up a 2D domain is that every surface, as I mentioned previously, has two directions. It has a U direction and a V direction. So we want to tell it how many subdivisions we want to have in the U direction and how many subdivisions we want to have in the V direction. That's what we can do with a 2D domain. So the domains are all, and I will actually, at this point I will actually highlight, if this sounds completely strange to you, there's actually a pretty good tutorial that I just found online, which I will send out the link to, and it's on deepprocess.org/grasshopper tutorial on surfaces, and it deals with domains and parameters and isocurves. So I highly recommend you watch this tutorial if you're brand new to Grasshopper and don't understand the idea of surface domains yet. So this is a 30-minute tutorial. But anyway, now that kind of assuming that you have watched that, so we will set up a 2D domain. Domains can be found under the Math tab, all the way in the front here. And basically what we're doing is we're going to take the surface, which by default has a domain, and we're simply going to divide it into several U's and several V's. So I can Grasshopper is smart enough to convert a surface into a domain. As an example, I'm just going to show a really quick example here where I will create a curve in Rhino. Or actually, I'm just gonna take these curves here, and I will show you that a curve also has something called a domain. But of course, it's only one directional. So let's just hide this for now. If you're not interested, you can just skip forward by a minute or so. But so here we have our three curves, and what I can do is I can analyze the curve and I can evaluate the curve. So basically it's asking me for a parameter on the curve domain to evaluate. So I can put in my curves and I can put in a variable. Let me just set up a slider to go from 0 to, I don't know, 2 to 10, for example. So here's a slider, and as you can see, now I can at domain point 0, we're all the way at the front of the curve. I'm actually going to extend the slider a bit, maybe go up to 50, and now we're at domain point 20, 30, and then eventually towards 50. So this, so the size of these curves is about 55, and 75 or so. So that's the domain. Now the surface domain goes from 0 to 64 in one direction and from 0 to 62 in the other direction. Again, I can show that by simply converting. Grasshopper is very good at converting things. I can simply convert a curve into a domain, for example, and this will show me from where to where the curve ranges. And I can also convert, of course, a surface into a 2D domain. So here it shows that for the surface, the U domain goes from 0 to 64 and the V domain goes from 0 to 62. Alright, so now, like I said, this is going to be the input for our domain that we want to subdivide further. And what this does, U and V by default are set to 10. That means it's going to create 10 by 10 subdivisions, which means it's going to create 100 values. And you can see, actually I will show you one more trick. Since these curves come from Rhino, the domains are kind of unknown. They're basically just based on the curve lengths. If I were to measure the length of the curve, I'm pretty sure 58, 56, 64. Actually, it's not quite the same. So I never really quite know where this domain comes from. But what you can do in Rhino is you can reparameterize a curve. That means the domain always goes from 0 to 1. So if I right click on this and reparameterize it, my domain goes from 0 to 1. Of course this is far too large now, so now if I were to create a new slider to go from 0 to 1, 0 is at the start point and 1 is at the end point. So now this is a bit better. We will do the same for the surface actually. We're going to reparameterize the surface, which means the 2D domain of the surface now goes from 0 to 1. Here's the proof. So with that, if we were to create a 10 by 10 division, the first subset of the curve of the surface, this is the surface we're talking about, goes from 0 to 0.1 and from 0 to 0.1. So let's say if this is our start corner, it goes 10% in this direction and 10% in this direction, and this would be our first field, etc., etc. So now we've created kind of 100 values, domain values, and we're going to use those to subdivide the surface. And if I preview this component, you will kind of see the subdivision edges. It's important in Grasshopper to always unpreview pretty much everything except for the component you're working on, because it just gets pretty confusing otherwise. So you see, now I'm actually going to set up a set of two sliders, which I want to be variable input sliders for the U and V domain. So let's just say I want to have one that goes from 5 to 20. Actually, both of them. So I'm just going to copy and paste this. I'm going to call this num panels U and num panels V. Okay, so these are my inputs as well. Put that in here. Alright. So now that I have my subsurfaces, I mean, all this really creates is just, as you can see, if I set this back to 10 by 10, it simply creates 100 untrimmed surfaces. So it creates 100 really small surfaces. Now for each of these surfaces, if I go back to my instructions, I'm going to find the centroid of each of these subsurfaces. So under the surface analysis tab, there's a area component, and the area will find not just the surface area, but it will also find the centroid. So there we go. And next I'm interested to find out the normal direction at that centroid. So I'm going to there's actually another kind of trick that we have to use here. We can evaluate a surface, and so if we evaluate the surface, it's going to ask us for the UV coordinate. So let me just find you an example again before we start using this. So this is my surface here, and I'm going to create a point that has two dimensions. The z dimension is going to be 0, and the x and the y dimension are going to be between 0 and 1. So here we have a point which of course sits now at, you know, very close to our origin, but I can turn this into a UV coordinate simply by connecting this to here. So here, let me just show you what this looks like. So the point has the coordinates 0.25, 0.25 and 0, and I can put that onto my surface, which I reparameterized previously. And what that will create is, yeah, let me just preview the surface again. On that surface at 0, 0, we're all the way in the bottom left corner. This is now in the direction of the y direction, or the v direction of the surface, and this is the x direction of the surface. So at 0.5, 0.5, for example, would be exactly the center of the surface, etc. So you get the idea. So this is how we can describe a UV coordinate of the surface. So now there's two ways of finding this. The first way would be, we could simply just set up a point that just called 0.5, 0.5, 0. Or I could set my sliders to 0.5, and I could put that here, and I could input my surfaces in here. Oh, interesting, this doesn't work. So instead of doing it this way, I would have thought that it does it for every surface. I may have to, again, reparameterize every surface. Yes. So in order to do it for every single surface, I actually have to reparameterize them again, because otherwise they keep the domain of the original surface. But instead of doing this, what I will do is I will take the centroid and I will find the closest point of the centroid on that surface. So surface closest point, surface CP, and what the surface closest point. So again, these are my surfaces. These are my points, which should exactly be at exactly the same location. But what it gives us is, it gives us a UV point on that surface, and that UV point now can be used as an input for the evaluate surface component. So now the evaluate surface component gives us the surface normal, and you can see it also gives us kind of a plane here, this frame here. Okay, so I will actually start documenting this quickly. Okay, so now that we have found the normal, let's look at our instructions. Find surface normal at the centroid, create a vector of a variable length in the direction of the surface normal. That's easy enough. So we want to create a vector in this normal, in this direction with a variable length. So let's again set up a slider. I don't know yet how long it should be. Actually, I will create a slider based on that is a certain ratio of the diagonal length of the surface. Should we do that? Or a certain ratio of the area of the surface. Let's just do that. Since we already have the area up here, let's just create a slider that goes from 0.1 to 0.25 to 0.5. So here's our slider between 0.1 and 0.5. I'm going to move it up to the front, remove these guys, and this slider will be called the Truss Depth. And I will calculate a percentage of the area. So I'm simply going to divide the area. So here we do some simple math. Divide the area value by that slider. So this just gives us kind of a smaller value. Sorry. It should of course be multiplied. And now this is the amount by which we want to move that point outwards. So we're going to create a vector from a start point in a certain direction. So we're going to create a vector from a start point in a certain direction, and we're going to change its amplitude. So the vector would be our surface normal, and the amplitude would be this value here. And now we're going to take this vector to move that original centroid point, or we could also just move this point here, it's the same point, in the direction of this vector. So we go over to transform, and under Euclidean we have a move command. And we can move, again, move is asking for two inputs, base geometry, which would be our point. So I'm just going to take our original centroid to be moved, and T is a translation vector. It should really be called V. So I'm taking this vector here. Oh, that's huge. So I'll make this range a lot smaller. Let's just make this maybe something like that. Okay, that looks a lot better. So so now that we have created this point here, all that's left for us to do, we've created the vector, we've moved the centroid in the direction of the vector. Now we want to extract 4 corner points of each subsurface, and then we want to connect them to the copied centroid. So let's go back to our subsurfaces, and let's extract always the 4 corner points. So that would be an operation under surface. So we want to actually analyze the surface for its corners, right? Sorry, we actually want to I think the best way to do this is to explode the surface, because when we explode all of our surfaces, we're getting all the edges, which you can see the number of edges is always 4 for each surface, and we're getting all of our vertices, which is also, there are 4 vertices in every surface. And the last thing we want to do is we want to connect these 4 vertices. So let me actually label this and take a different color to do that. Subsurface corner vertices, and this would be our, bottom point of the truss. And we want to connect them. Now there's one kind of thing to be cautious about, and you can see how the line type has changed. And again, if this is completely new to you, if you haven't watched this seen this in any of the tutorials that we previously had asked you to watch, then I highly recommend you do this tutorial on surfaces, and you may even want to go and take the very first lesson, which talks about that. So if this is completely strange to you, please watch the first lesson and then the Grasshopper tutorial on surfaces. And they also have a continued surface tutorial, which actually creates some pretty cool effects. Something that you may actually want to be using for your homework. Alright. So now this line here is grafted. That means we have, as you can see, actually I can visualize that using this component here. I can visualize my tree, and you can see that we have 100 lists, and each of these lists has 4 objects, 4 points. And so here's the list count, and here's how many points we have in every list. While here we have just one list with 100 points. So what we need to do is we need to match the data. So we need to create as many lists from here as we have here. So that we can do by simply grafting the component. I can right click on it and press graft, and now we have 100 lists in here, and we also have 100 lists in here. So now what we can do is we can simply connect points from list A and points from list B, and it will create those 4 lines for us. So this concludes the first. Let me just preview the edges. We're also interested in seeing the edges, so I'm just gonna put them into a different line placeholder here. Sorry, curves, they're not lines. I may want them to be lines actually. If I wanted them to be lines instead of curves, all I would do is I would create polylines. Let's just do that. Because I want them to be straight and not curved, I'm going to create closed polylines from these vertices. So I'm going to draw a polyline through these vertices, which is going to create 100 polylines that each have 4 points to make sure that they're actually closed. So I'm just going to create a panel that says true. And the next thing is that so now that we have these polylines, I'm just going to explode them. And this way I have my straight line segments, 400 of them in my example. So this is it. This is the first part of the tutorial that we went through last week in class. So at this point I'm going to save my Grasshopper file and I'm going to clean it up, and then I will show you also how to create some roof analyses. Okay, so I'm going to clean up this definition before we go into step number 2. So all my 3 variables that I have are labeled and they're on the left hand side of the definition. I always want to set up my inputs on the left and my outputs on the right. So I'm happy with this. So I'm just going to group them using the input color. Didn't work out. So now I'm going to label what the steps were that I actually did. I'm actually going to write a few small tags here. So the first one would be Subdivide Surface. Create and subdivide surface. So if I move this, you see if I kind of pick it up and start moving it, it feels kind of funny. So instead of doing that, I can hold down my shift key and then it will move and it won't rotate. So I can move it wherever I want. So let me start grouping things. Loft and reparameterize surface. Divide surface domain. And create subdivision surfaces. Or subsurfaces. Find the centroid. Then what we're doing here is we're finding the surface normal. At the centroid. Then we're creating the bottom points. And then we're just grafting it to, in the end, create our sets of four lines. And here we're creating linear surface edges. Okay, so all of these things are operations. I guess I can, let me just label some more things. Copy and paste this, move it over here. Let's just say create trusses. Okay. Now I'm going to create some larger groups in a semi-transparent color. Actually, let's group this as well. And this would be maybe another step, surface normals. I'm going to right click and add that to the group. And so this would be number 3. Okay, so my outputs, my really important outputs for the analysis should be, of course, actually, my outputs for this whole definition should be my surface edges and trusses. So I'm just going to combine all of this into one placeholder, one line placeholder, holding down the Shift key. All of these are now my trusses. Actually, I want this to be in red for output, so I'll take this color. Truss edges, or truss lines, center lines. So if you guys want, you can pipe them. I find that it makes the surface, the model a bit heavier, so I'll just leave it. Also, what is important to me is, just for the analysis that we're going to do next, is the area value and the centroid location. Okay, so area and centroid are also important to me. So I'm going to create 2 additional outputs here. One is a number and one is a point. Surface area surface centroid. And lastly, what I want to do is I want to do my analysis and then I want to visualize it by color coding the subsurfaces. So I'm going to come all the way back here and take my surfaces as well. Yeah, this, I don't really like where this is going, so I'm actually going to just change the wire display to hidden. I don't want to do this too often because then I don't understand anymore where anything is connected. Like here it wouldn't make sense to change it to hidden, but sometimes it just does. So I have my subsurfaces, I have my surface centroids coming from here, and my area values coming from here. And I will hide all of these wires. And I will move this up. And also what we can do is we can select all of this, and we can arrange it, array it all to the right, for example, and then space it equally. Okay, so now everything else can be hidden. It is. And now I'm going to actually take these as an input for my surface analysis part. So for now, let's take the white background as a new group and group all of this. And give this also a new headline. So this would be the roof truss geometry. And next we're going to create roof analysis. So I'm going to copy all of these because I now want them to be my inputs. So I'm going to copy them, create the outputs from here to here, make sure all the wires are hidden, and change the colors and the group sizes. So the hue for yellow is 60. Hue value is 60. And down here, I don't think we need the center lines actually, but I'll just move them down for now. So, like I said, the first analysis will be area of the roof. So, I'll simply take this area value, and I'll use that to color my subsurfaces. So, let's find the gradient, and I want to set up, by right clicking on it, I can set up a 3-color gradient. So let's go from red to blue, and so basically my values that create these colors are driven by the area value here. So these are my values. Now I want the smallest value from here to drive what should be red, and the highest value from here to drive what should be blue. So if I look at these values, there's some 30s, some 20s. I don't actually know what the domain is, but again, these are all values, and I can look at the domain of this, which means I can create a domain, and now it tells me that it goes from 18 to 45, and then I can just take the domain components, and the smallest component, the domain start is 18, and the domain end is 45. And what this now does is it generates, based on those values, it generates RGB values for me, color values, and I can take these color values and preview the surfaces based on these. So there's a color preview under vector, and it has 2 inputs. One is for geometry. My geometry would be my surfaces. Let me just move this to the top. So by default it just previews it in pink. And my shading would be this color here. And if you wanted to add some transparency, we could do that as well. So then we would just set up a material and the material can have a transparency value. So there you go. So this is the first analysis. Now we've basically recreated everything that you did with Justin in class. And since we're here visualizing things, I'm going to move this over here and change the color of it. But instead of just having one visualization, I want to create a second one for the elevation that measures the elevation of the surface center point. So in order to do that, I will just take the center point, and I will decompose the point into its 3 components, and I will take all the z values, and I will simply use the z values as an input for here, and also as an input for here. And now you can see where it's low, it's red, and then the higher surfaces are colored in blue. If I don't always want to switch 2 inputs, what I can do here is I can just take a number placeholder, and I can put this in here. I can make this, put this in here and in here, and now I can simply switch what my input number should be. So let's just say, so I'm going to name this guy, this is going to be an input. And this will be my color values. So color color driving values. So they could either come from the z coordination, or they could come from the surface area. So the larger panels are in blue and the smaller ones are in red. And lastly, actually we can do something fun. We can start playing with our sets, and we can set up a stream filter. So we can say, based on, I can either say go take the inputs from gate 0 or take the inputs from gate 1, and I'll put them in here. So now I could just set up like a slider, for example, that goes from 0 to 1. And I can change which analysis to run. So an even better example of doing this, instead of calling the analysis 0 or 1, what we can also do is we can set up a value list. And you can see we can have a preview, and we can have a numeric value or some kind of value coming out. So if I double click on this, if I right click and edit this list, see on the left is preview. So let's just say let's just see. So surface area would be 0, and elevation would be 1. And if I wanted to set up more, so for example, distance to attractor, I'm going to set up an attractor point now. Would be analysis number 2. So now I can put that in here. I can choose from the drop down whether to use 0, 1, or 2. Now of course 2 doesn't work yet. And I can call this my analysis type. All right. Okay, so the next point is I want to set up in Rhino an attractor point, and I want to measure the distance between the attractor and the centroid and color code the surfaces based on that. So in Rhino, I don't know why my escape button doesn't work anymore. So since I can't go back to Rhino for some reason, I'm stuck. Yeah, I'm stuck in Rhino for some reason. It's because I'm recording the screen and it doesn't work together. So so I will just set up a point with 2 sliders on the XY plane, or whatever. I'm gonna draw a circle. Whatever. I'm gonna draw a circle in Grasshopper and just make a point go around the circle. So I just want to create some sort of attractor point. Why? Actually, here's an idea. I can create a box. Let's see. I can create a bounding box. No? There it is, bounding box. Around the entire surface. Oops. Not per object. Okay. Now from this box, I'm only interested in the bottommost surface, either the bottom or the top surface, and then I will just create a point on that surface. So let me just take find the bottommost surface. So I'm going to explode the box. Explode this box poly surface into 6 different faces, and then for every of the faces, I'm just going to now take the face that has the lowest elevation, because I'm interested in the bottom face there. So I'm going to, for every face, I'm going to find the centroid. So for every face, I'm going to evaluate it at 0.5, 0.5. We always have to reparameterize them. So here we go. Now I have a list of 6 points, and I want to find the point with the lowest z-value. So I'm going to extract the z-values from all of these points, and I'm going to sort them. And I'm also going to sort the surfaces in the same order. And I'm going to take now the first surface, which is at elevation -4. So I'm going to take one item from the list of surfaces. So here are my sorted surfaces. Here are my sorted surfaces. And I'm going to take only the first item. So if I unpreview all of this, I end up with this surface here. And now on this surface I will create a point. Give me a minute. I haven't done this maybe ever or in a long time, but I want to use the MD slider, the multidimensional slider, to basically create a point on that surface. So, actually, yeah, we can just use the same command here again. This would be our surface, this would be our UV, and if I preview the point, here we have a point now. So we can kind of control where on the surface the point is using this 2D slider. So lower left corner, upper right corner, etc. Okay. So much work just to get a point, just because I couldn't minimize Rhino, so I couldn't actually draw a point in Rhino. But this could also be a point from reference in from Rhino. So yes, all of this has been done simply to set up an attractor point. Okay, so I'm going to clean this up for a second. Actually, now that this is taking up so much space, I will reshuffle things. So bear with me. I'm just taking the subsurfaces from the top, and here we go. Make this font size 70. And group all of this. Alright. Change the group color one more time and group the inputs. Move this to the background by clicking Ctrl B. So here we go. Inputs on the left in yellow. Make sure this big box is part of the white box. So I right click and add it to the group. And now on the right, this is my attractor point. Whoa, so much work. So I'll take the output color, make this the default color, and group it. Change this to the B in the back. Add this to the group, and call this attractor point. And now the attractor point is going to become part of the inputs for the analysis. So here's our attractor point, and now what I want to do is I want to add one more analysis type, attractor distance. So I'm going to zoom in, and now I can click and add another input, number 2, which this will output number 2. And I will put in a value of distances between the centroid points and the attractor point. So I'm just going to go to vector and measure the distance between all of those points, all of these points here, and this red point down there. And those distance values are now going to drive basically the coloring of the surfaces. So let me turn this off again. If I go down to attractor distance, you can see the further away, the more it leans towards blue, and the closer, the more it leans towards red. Now if we go back to our kind of panel here, we can now change which elements are red and which ones are blue by moving the point around. Okay, so let me just clean up this definition and then we're done. Okay, this is, I think, all pretty self-explanatory. This last bit here, the analysis is very simple. So, as Justin mentioned in the homework, as part of your homework, you should come up with some of your own analyses. So, so here, please just add a couple more instructions. I don't know. You could come up with maybe some interesting math. Simple stuff like multiplying the area of the panel by its elevation value, or maybe something more interesting. I could also do something like, instead of taking the elevation, I could take the x or the y axis, the y value. So instead of taking the z value here, if I take the y value and set this to elevation, of course, it just kind of goes in one direction. So elevation is a bit more interesting. But I hope that you can come up with a couple of nice examples here that to add to the roof analysis and to add to this component here. Thank you very much. Bye-bye.